this idea that we are doing this week effective interactions from first principles or microscopic. And so I am talking today on ab initio leading order effective interaction for elastic scattering from of nucleons from light nuclei. I list here on the screen also my collaborators. And the first author is Matt Burrows, who is my graduate student and right now writing up his thesis. Robert Baker is our postdoc, and Steve Webner, Christina Lowney, Peter Maris, and Gabriela Popa are collaborators. So I start out, since we are a reaction community, I start out with a very short introduction here. We have heard in the past weeks a lot about reactions, specifically exotic nuclei. They are short-lived, so you have to study them in inverse kinematics. And for example, in direct reactions, you start with some initial state, you have a reaction mechanism, and you have a final state. And the entire challenge of the reaction is that in the continuum, the theory can solve the few body problem exactly, but we are dealing with many body problems. So we have, as I did in the cartoon, so we have to do something to map a many body problem onto a few body problem. For a very specific part is here, for example, a DP reaction. This graph here is the typical graph you write down. You have a deuteron scattering of a nucleus and you approximate the nucleus by a blob. And then you solve the few body problem. Of course, when you do that, you have to define a Hamiltonian for the effective few body problem, which is kinetic energy, your NP reaction, which is between the neutron and proton in the deuteron. And then you have effective interactions between the neutron and the nucleus and the proton and the nucleus. And so now if we talk about interactions and really questions what we are doing, we believe today that the nuclear-nucleon interaction is well known. And today we're using chiral interactions of different flavors, different renormalization, but we think we have this under control. But then the effective proton or neutron nucleus interactions is on a much less theoretically secured footing and not as developed as the nuclear-nuclear interaction. Most of the time, and purely phenomenological optical potentials are used, they're fitted to data. And sure, we always need data to do that. Then there are optical potentials with theoretical guidance, where you put in some of the structure information you know, or you have microscopic optical potentials. And this week, Jin wanted to have two different approaches to microscopic optical potentials, though I prefer to use the word optical potential more towards only for the phenomenological. So what are we doing? If you isolate relevant degrees of freedom, there's a formal way of doing it, and it's called, you separate the Hilbert space into P and Q space, you do your calculation in P space. And the projection on P space requires introducing effective interactions between the degrees of freedom that are treated explicitly. And the person who already wrote this all down was Feschbach in 1958. He also said, what comes out of that publication is also the insight that these effective interaction made by projecting out the Q space are non-local and energy dependent. That is already a statement which is not totally consistent with what is often used. Namely, phenomenological optical potentials are energy dependent. They're either fitted to a global data set or restricted data set. Most generally, they have the form of a Wood-Saxon. And it's a function, a V of R, and an imaginary part, and operators dealing with that. And basically, since they are only functions of R, they're always local. They have a central and spin-orbit term. They're fit to cross-section, angular distributions, polarizations. And usually, the lightest set of nuclei in this fitting is carbon-12, and they're doing very well. They go up to lead and stuff. The disadvantage here is, of course, if you fit to the reaction data set, but you have no connection to a microscopic structure theory. The onset of changing that are dispersive optical models, because there, via the dispersion relation, you connect for negative energies to the structure information. So now, what can one do to be more microscopic? And so there are two things. I mean, it's because we also have to realize something. Today, a huge progress in ab initio structure calculations has been made. And so one should have the goal, if we want to construct effective interactions, we want to construct them from using those ab initio method and the developments there. So if you want to do that one, we have to start from many-body Hamiltonian with 2 and 3 body forces. And again, the foundation for doing this was, interesting enough, already laid in the 50s by Feshbach and Watson. Feshbach suggested to have effective NA interactions via Green's functions from the solutions of many-body problem using basis function expansion. There are different methods and stuff, and there has been done a lot of progress. And we will be hearing tomorrow, on Thursday, by Andrea Edini on their approach just based on this, calculating effective interactions. Another piece of work was for heavier nuclei done by Jimmy Rotaru et al. For calcium nuclei using the Gamow-Shell model. So basically, one of the things is, if you solve Green's function expand in bases, at present, because of the size of the basis you need, you are more restricted to the lower energies. So this is basically, you see here the energy, this is 5.2 MeV and this is 3.2 MeV. So that is a Feshbach approach. I am following the other approach which was laid out by Watson. Watson decided that to do a multiple scattering expansion, for example, the spectator expansion, which was formerly then refined by Siciliano, Thaler, and Pickelsheimer and Thaler. But basically what it is an expansion, a diagrammatic expansion. So since I'm coming from the few body, this is more along my line of thinking. I like to think in expansions of theories. And the current implementation of all of this ends at 2 active particles. And so the expansion is basically in particles active in the reaction. What is also done, and we antisymmetrize in the active particles. That has been pointed out by Watson already, and it is in his book, that basically antisymmetrization active particles is an antisymmetrization in the order you are working in, but it's not an antisymmetrization as, for example, it is done in the Feshbach-inspired model. So if you expand in the number of active particles, the idea of Watson was to use this for fast reactions. Fast reactions, of course, changed over time. When Watson expanded it, this was really 100 MeV. Then further on, I mean, it was used at 200 MeV, 500 MeV and stuff. But basically, this expansion is an expansion also in energy, and I will tell you exactly where points in, which gives you an energy limitation in the practical implementation. So let's go in. If we do that, what do we start out with? We have in and out states of the target. We use here, if we do elastic scattering, we use the ground state. However, I want to point out, one can also project on other states. Point is, we are constructing a projector, P, and P plus Q is equal to 1. What we need to have is that the free Green's function, which describes our motion, commutes with P. And so for elastic scattering, we project on the ground state. Doing that, we can write a Lippmann-Schwinger type of amplitude, namely that T is U plus UG0 PT. That should be the equation we are solving in P space. since we are introduced here in the general equation here, the 1 with P and Q, we get as potential a V, which and G0, and we have the Q space in here. So this is the exact expression and definition of an effective optical potential. Now, that doesn't help you very much. You have to do now the expansion in terms of active particles. I wrote here how you could think about it. You have always one particle coming in that is your projectile, and then you scatter off nucleons in the nucleus from 1, from 2, from 3, and so on. And so basically, we wanted to kind of then work in a spectator expansion of the effective potential. And we only do the single scattering. And so single scattering would be you scatter from one nucleon and you sum over all of them. And I write here on purpose a tau, because whatever we are having here, there is this Q space which one has to deal with. And so let me talk here now about the two operators in this equation for the tau, where one has to think about. Basically, dealing with Q, you cannot or should not use here the free nuclear-nucleon T matrix, because we are in Q space. So we dealt with that by introducing basically an operator, the free T matrix, and connected to this operator tau by an integral equation. You can easily solve that integral equation. If you said already, I should say I'm working in momentum space, and so integral equation solving is standard there with all its complications. But if you solve one integral equation, solving an integral equation again is no computational extra work. However, you already see something here. Taking integrals means always averaging. That by treating the Q space in this fashion here, by solving the integral equation, connecting the free T to this tau inside the nucleus, averages over all kind of Q space. That means that is already a lower limit of the energy you could use, because this does not take care of about separate resonances, low-lying resonances. That is already averaged out by this approach. So that sets basically the lower limit. The advantage of that is that you can actually have now separated out. You have n times n neutrons in a nucleus and z protons, and so you can clearly separate the contributions from the protons and the neutrons, because, and that is specifically important now in our area where we look at exotic nuclei, where the density distribution of the protons and the neutrons is different. And of course, the proton-proton and neutron-proton T matrices are also different. The other issue, what we have to look at, G0 is in principle a many-body operator. To turn this into an easy-to-solve few-body type equation, one usually uses closure to obtain a two-body propagator, which means, again, averaging out all excitations in the Hamiltonian. And so these two things, treating Q and G0, for example, by closure, they limit the lower energy this theory is valid. And I thought I really should point this out to get an understanding what is in the theory and what could one expect. So let's look at what the first order term actually looks like. And for that, this is this term here. And I like to write this handbag diagram, because if I go in the center of mass, I have here the momentum of the incoming projectile. This is my momentum of the nucleus. I'm exciting one, I'm hitting one of the nucleons in here, and I have to integrate over this. And here is the two nucleon interaction. And basically, so my potential looks like it is a three-dimensional integration over this. And I wrote the variables like here, but we are using variables. One variable is always the momentum transfer, and the other variable is the average momentum. So I have to integrate over This is the NN scattering amplitudes on the potential and depending on the form we are using. And this is a nuclear one body density. And point is what we can do now, and that was where I call it now ab initio, that the same NN interaction is used here for the nuclear-nucleon force, as well as the one body density. They both are derived from the same underlying NN interaction, and that's why I start calling it ab initio. I have worked on, there's a lot of work on how to deal with actually in the 90s. However, in the 90s, we have high precision nuclear-nucleon potentials, but the nuclear structure, mainly what was available were mean field calculations. Okay, you also can look at this one here if you just stare a little bit at the equation. First of all, it's non-local. It depends on two momentum variables, and it depends on the energy. And this is the energy epsilon of it's the T matrix plus some additions, because as you see, this is really a fully off-shell integral where conditions of the density as well as the T matrix enter. And the details of the current implementation, I always say, is designed for energies at 100 above 100 MeV. So now let's go a little bit further, and to actually understand what one has to do, let me go to the nuclear-nucleon T matrix. I would like to look at it. This is the T matrix. It's related to the scattering amplitude. There is, if to be very general, it is often useful to look at the operator structure. And the operator structure is nicely given in the Wolfenstein representation. And if you see this here, I am writing, so this is the scattering amplitude M, and it has 6 terms, and on shell only 5. And so I write it now in a not so usual textbook form, but I write every expression which has to do with the projectile in blue and everything which has to do with the struck nucleon in red. So I have here, well, this is the central amplitude. Then this one here, normally you would write sigma from projectile plus sigma from the other nucleon is a total spin. And you have the spin dot n hat is the LS operator in momentum space. So this is basically the LS amplitude. And then you have 3 tensor amplitudes. Some people may recognize this piece here that looks very much like the 1 pion exchange. But what it actually is, you take the spin and you look at, I've made this little figure, not very sophisticated here on the bottom. You have the momentum transfer and the average momentum. They define a plane, whatever I'm doing. And then this R3 is determined by 3 momentum vectors. So you have to put the, you take the cross product, K cross Q, and you have the 3rd vector. And this is the space. And now you can take any orientation of a spin of a spinner and project it on the 3 momentum directions. And these are the operators which you see here. This operator here is basically, if I mix this, it is 0 on shell, because if you set P prime equal P, then these terms vanishes. And so if you look at nuclear-nucleon scattering deals with these 5 Wolfenstein amplitudes. And they have names, the functions have names. And the functions themselves are functions of 2 momenta and an energy. So, and you see already where actually the problem is if you want to do that for an effective potential. Projectile 0 lives in a plane wave basis. We have been doing scattering calculation in plane wave basis forever. But now we would have to do, if this one here, the red pieces, this, if we want to truly evaluate this, we need to evaluate the scalar product, sigma I, inside the nucleus, and that requires a spin-dependent one-body density matrix. That is usually not done. And so we did this, and by doing this, we defined basically a non-local one-body density matrix directly in momentum space, and we defined a spinor inside directly into the definition so that we have it cleanly isolated. So now if you look at this in tensor representation, this is the tensor index, k is equal to 0, then this operator becomes 1, and you recover the scalar one-body density matrix as one always had. For k is equal to 1, you actually have a spin-dependent one-body density matrix. Okay, we can do that. But then we also need to calculate the projections of this spin here now along the different momenta, n hat, q hat, and kappa hat. So, doing that, we named the functions s for spin and then projected here along n. I give you only one expression for that. So luckily, it turns out that you have that you can pull this n, which is in the center of mass, given in the center of mass of the nucleus. You can pull this out and you can evaluate this. It's a gigantic thing. I don't expect you to really look at the formula. That's the answer. But basically along the way, we always have to change variables into q, which is a translationally invariant variable, and the average momentum. And that is very convenient because when you come from a no-Koshel model calculation, you also have to remove the intrinsic center of mass motion from that calculation. So we have then the function Sn of q. I leave out the energy here. And what you actually see, so lots of Krebs-Gordons and stuff, but I just want to point out here, that is the input which we actually get from the no-Koshel model, namely the reduced matrix element. There's a lot of technical details. You can go on the web and look at this one. This factor here, what you see at the end, that comes from removing the center of mass. So we can do that for Sn, which is the spin projected along the normal to the I call scattering plane. And then similarly, you calculate the spin projected momentum distributions along q hat and along kappa hat. And you discover that both give 0 contribution. Numerically, we checked it, but you can also think about it. Because if I go between, I mean, this is a matrix element. If I go back up here, you have, this is the general expression. I have a state, maybe the ground state, and some other state phi prime. But the point is, depending if I do now scattering and scatter from the ground state, or if I have left and right the same state, they have the same parity. If I look at here, sigma is a pseudo vector, and if I dot and hat is a pseudo vector, so this one here, this product here is parity invariant, while if I do sigma I pseudo vector dot vector, and here they are not invariant under parity transformation. So if I have the left and right the same state, those contributions give 0. If it's not the same state and they have odd parity, then they would contribute. So now let's go further on. What is actually now contributing into the calculation? I rewrote this here a little bit, that here I have here the 1, this is the central amplitude, this is always there. We have here the C, where here the spin sigma 0 dot n hat and a 1 in in the nuclear space. And then I have here these 2 contributions which now have to be considered. And what you see also here from the nuclear-nuclear interaction, this is the central part. This is the spin orbit part of the nuclear-nuclear interaction. And this is basically a tensor piece. So now we are, and those other, so only the Wolfenstein amplitudes A, C, and M actually contribute. G, H, and D do not. So now let's have, before we go, let's actually have a look how Wolfenstein amplitudes look like. We are using, for the entire calculations here, we have only used the N2LO opt potential. For one good reason was that they give already reasonable radii at the 2-body level, and the 3-body forces are via fit and construction relatively very small. So now this N2LO up potential here, I show here Wolfenstein amplitudes, A, C, and M at 100 MeV. That potential, the N2LO up potential is fitted up to 125 MeV. And so you can reconstruct that and calculate this, that this would go to a maximum momentum transfer in the scattering to 2.45 inverse Fermi. So when you look this up here, the red line is N2LO opt. And I compare it here, for example, with CD-BON, which is one of these high precision potentials and being viewed as a representation of the data. I also put in here the dots are the extractions of the Wolfenstein amplitudes by the GW Institute of Nuclear Theory, basically Workman, Briscoe, and Stokowski. And to give you also some idea what experimental extractions give you. Because again, Wolfenstein amplitudes are not unobservable, they have to be extracted from data. And so when you actually see here, this is N2LO opt is doing reasonably well in comparison. The only thing what I want to point out, it's always here the spin orbit piece is a little bit over predicted, but not too much. I also want to point out something that, for example, in both NP and PP, the real part of C is very small. But if you go back to the formula here, there's always, with the Wolfenstein amplitudes, is there an I? So for the spin orbit potential, it's actually important how the imaginary part of the amplitude C looks like. Okay. Obviously, if you go to higher energies, the disagreement of N2LO opt with extracted data or CD-BON gets worse. So now let's look at it. Now it's time to look at, we put this all in, and I thought I had one more slide, but apparently I don't. So I have to go back. So what we are having now, the optical potential has now pieces which are the central piece, the spin orbit piece as we had. If, and this is the only thing which you have if you neglect the spin of the Stark nucleon. If you include it, you get 2 extra pieces. You also have to realize that now at the we have to include these pieces for the neutron protons, for the NP interaction and for the PP interaction. So what we are getting from the no-core shell model calculation is neutron distributions and proton distributions. So let's look at some answers. Okay, and so this is one of the things I was interested in. Was that we have done microscopic calculations for a long time, since the 90s or 80s, and always neglected the spin of the Stark nucleon. And the argument was quite heuristic and said, well, if nuclei are closed shell, then the spins kind of line up anti-parallel, and in the Nmax 0, lowest order approximation you can actually show for a totally closed shell nucleus, all spin contributions analytically all cancel. Obviously, for a true no-core shell model calculation where you go to very high Nmax and allow excitations above the lowest shells, that's not the case anymore. So basically, I show here helium-4, and I have 2 lines in here which you almost cannot distinguish. Because looking at closed shell, we see that the approximations from the earlier days, neglecting the spin of the of the Stark nucleon, was very good. And so here again, this line is at 2.45 Fermi. You should actually only look up to there, because that is where the N2LO opt is fitted. So it's basically we're looking at forward direction. Nmax 18 for helium-4 is high enough so that there is it's fully converged. The different H bar omega convergence, no-core shell model, you always have to check on different values of H bar omega. Here it's 20. However, if Nmax is high enough, they should all converge to the same line, and they do. So here in helium-4, it's a very large calculation. It's fine, converge. For oxygen, it's not. I have in the backup a slide if somebody wants to see how the spread with H bar omega is, because Nmax 10 is the largest we can do. But point is, I mean, the point I want to make here, what the old people and those before us did as approximation is very good. Now let's look at the other one. Let's look at open shell nuclei. And so I took here helium-6, helium-8, and carbon at 200 MeV. And we were somewhat disappointed because it looks like as if the spin of the struck nucleon doesn't matter that much either. Certainly at this energy, you see something here at helium-8. Carbon-12 is amazingly unsensitive to the spin of the struck nucleon. And we thought, well, we should do it for carbon-12, this calculation. So now, before I go on, I specifically state here at the higher energies because what we also have to ask, if there are extra spin effects and stuff, at what energy do they show up? It's not only if they're there, since these potentials are energy dependent, we also have to look at what energies they show up. Before I go on, I also wanted to show something, namely reaction cross-section versus extracted point proton radius. Because one of the things what we actually should be looking at is now, there are reaction observables and there are structure observables. And if you want to combine like reaction and structure theory, it will be nice if you can correlate observables from one area to observables from another area. And so we did this here for carbon-12 and for oxygen-16. Basically, there were reaction cross-sections at 230 MeV. So there are not that many experimental data out. We felt comfortable at to calculate at 230 MeV for the both nuclei. And what we are seeing here, it's a 200 and 230 calculation. And basically here we perform it at Nmax 6, at max 8, and Nmax 10 for different H bar omega. And the lines show the calculated point proton radius versus the calculated reaction cross section, and here the bands, and so that's, and then we can nicely extrapolate, and our extrapolations are actually, when we go here, this is the experimental error bar. Here's the experimental error bar. We also have here, this is our theory error. When extrapolating the calculations, obviously there's also an error in extracting the experimental point proton radius. So we see a perfect correlation here at 200 MeV. This is only surprising, and I show it for the reason is, if you do iconal at a lot higher energies, you can analytically show that they are correlated. Here now, when we're doing the ab initio theory, we get out the same thing. What you expect. I did not expect it that it goes that low, and so we get the same thing. What one should get. Okay, so now let's go back to our more closer look at what happens with open shell nuclei. And so I go back now to 100 MeV. Everything else I'm talking from now on is I'm going to lower energies. And here was the interesting thing here. I show here the closed shell nucleus carbon-12. Yes, there's a small difference between the full calculation. The full calculation is always a red line. And if you leave out the spin of the struck nucleus, it's a dashed line. Interestingly enough, we only see really some effects in spin observables. That's where you should see spin effects. And for the nuclei which are N not equal to Z. That was one of the surprises, that even carbon-12, which is open shell, but it's N equals Z, that their spin effects, the effect of the spin of the struck nucleus is quite small. Okay, we also did something else. We went into energies even lower than 100 MeV. And here it's helium-4 up to carbon. And we were very surprised. I mean, there are data, helium-6 and helium-8 have been measured extensively in inverse kinematics at Wickham. And we were very surprised that actually the cross sections, the magnitude is predicted, here in this case post-predicted correctly by it's a parameter-free prediction. So we were somewhat surprised because I am 71 is below my comfort level in the energies we should look at. Obviously, if you look at the spin observables, we see that I am justified to be below my comfort level. So we see again effects, but we cannot describe. There's something missing for doing the spin observables. So let's look at something else more. We have now done, I mean, this is what we see on observables, and we can look at them and be delighted about it. But the question is also, now we introduced this spin projected moment distribution. And so usually we should ask, can we learn something from it? So what we actually do, we have this function Sn of q kappa. If I integrate over d3 kappa, so about this off-shell momentum, I can define something like a spin form factor. Here it is transverse because it's the spin projected on the along the normal of the plane spanned by q kappa. And I just plot this thing. And so this is the one for the protons. Since here nm18, that means the n max, it's the maximum n max. I'm showing here the calculation h bar omega 20. But for helium-4 and helium-6 with a high enough n max, that is a line, it's converged. Here the shaded line for helium-8 means that shows the h bar omega dependence. So what are we actually seeing? One of the things we are seeing, I show here also the absolute value because actually this spin function also has a sign. And if you do a scalar product, if you project along a vector, it can be parallel projected or anti-parallel. But here, I just show the absolute value. And I also have to, for those who live in R space, let me just make the remark, something which is extended in Q space is smaller in R space. So what we are seeing here, number one, the numbers are really, really small. So there is, so the spin function is very small. We also see it doesn't change if I go along the helium chain. The physics, what we know is the helium-4 is the smallest, and the proton distribution in helium-6 and helium-8 gets larger, which means the momentum space is squished more. So we see something which you may think, well, we can see with other things too. So now let's do the interesting thing. Let's go and look at the neutrons. And so this is the neutron spin form factor, and you see immediately if you look at the side here, this is a factor of 10 larger. And to kind of make it easier, this one here is the neutron spin form factor of helium-4. It is actually here in the insert. I put it in the same units as here. So one of the things which you can observe also is that the spin form factor for neutrons and protons in helium-4 is almost identical. That means also, again, let me go to, I don't have a figure for that, but when we looked at this for the other n equals z nuclei, we computed oxygen and carbon. For n equals z, the neutron and proton spin form factor are pretty much identical. And so that means, and so that from that, I understand the calculations which we are getting, that we don't get any spin effects for if it's open shell or closed shell, if we move along the line n equals z. Now we look at this at the neutron spin form factor. And so this is helium-6, it's the red one, and helium-4 with h bar omega dependence band is and helium-8 is the blue one. So one of the things what you see here, for helium-6, 2 neutrons are added into the p shell. Yes, and I mean it's not 2, but it's the neutrons carry the spin information. Then I put on 2 more neutrons in, and I get helium-8. And again, it more than doubles. So that means also, I mean, so it's not So the spin here is the two the extra neutrons in helium-8 don't fill the 3p half shells and kind of align their spins parallel. No, the spins are, it looks like as the spins nicely add up. Okay, and so that's why in helium-8 we actually also saw the spin effects in the spin observables. So this is something what we could kind of see when looking at the spin form factors. Now I have one more slide, which is the no-Shell model in the symmetry adapted version. You can look at spin contributions and wave functions. And Robert was so nice to make that figure for me here. These are, you have helium-4, helium-6, and helium-8, and you can see in the wave function the contributions of the total spin. So it's always helium-4, helium-6, helium-8. So in the proton spin is pretty much spin 0 most of the time. So this is, you can, so they're all normalized, 1 is the max. And so most of the time for the protons, they are in total proton spin 0 state. There's a teeny bit spin 1 that is very consistent with the spin form factor which we computed. If you look at the neutron spin, oh yeah, there is helium-4, the neutron spin is also mostly spin 0. And then you see a spin 1 contribution developing for helium-6 and helium-8. And it is in the order of magnitude very consistent with the spin form factor tells you. Here is the total spin, neutrons and protons added together. So you can see here, helium-4 is pretty much, has mostly spin 0 contribution, some spin 2, because you also can add up the spins to a spin 1, and then also its vector addition, you can add it up to spin 2. And so here, helium-4 has almost no spin 1 contribution, whereas helium-8 has a lot. Helium-6 has same amount of spin 1 and spin 2 contribution. Obviously, the wave function is not an observable, but we neither are spin form factors. However, a spin form factor is a little bit easier than to compute once you have calculated all the densities and stuff. So we wanted to verify here is the information which we can see and almost automatically can extract now from the calculation. Is that consistent with what we're actually seeing? And what does it tell us about the helium isotopes? I mean, as a few body person, if I go back here and look at this, for helium-6 and helium-8 have been like the practice laboratory for like effective field theory and few body modeling, because we always look at the core, the helium-4 inside, everything is nicely paired up, and the physics is done by the 2 neutrons or the 4 neutrons. This one here actually is almost a confirmation that this is a good way to handle those helionuclei. I also would say probably go back when I said here that the cross-section were so good for helium-6 and helium-8 is probably related to the fact that this is a halo system, and so it's very loosely packed, and so higher order scattering effects don't show up here. Whereas if here carbon-12 and helium-4 are packed a lot denser, so we actually see even at a much lower momentum transfer already a deviation where higher order correction should come into play. So that was things we have been doing so far, and I should be coming to an end. So right now, I mean, there is a renewed urgency in the reaction theory community for microscopic input. For any kind of reaction calculations which rely on effective interactions or implicitly on some few body type methods. So so there is a renewed interest to actually do that, and do that as microscopic as one can do. And so most likely I see that there are complementary approaches needed for different energy regimes. And so basically with being very consistent in terms of the NN interaction used, it is possible now. So, and as I said in the definition, I mean, there are several definitions of ab initio, but the leading order term can be now calculated ab initio by treating the nuclear-nucleon interaction in the reaction part as well as in the structure part on equal footing. By doing that, we discovered, at least for one isotope chain, that basically effects of the spin of the struct nucleon become important if you leave the line n equals z. And so now we are looking at the effect of other isotope chains. Obviously, with no Kochel model and calculations, we are right now restricted to lower mass nuclear chains. What we also should really think about some more is how can we connect spin form factors to observables? Because again, our experimental colleagues don't measure form factors, they are extracted. But there could be another additional information about how the shape or how the nuclear structure actually looks like. Then we definitely still have to do the dependence of the NN force employed, because we plowed here through theoretical development. We stuck with one NN interaction. Of course, one shouldn't do that one. And then one can also think about refinements of calculations of the leading order term, namely taking more structure of the full propagator into account. That is options. And then there are some other, I mean, it's eventually you would like to at least try a going one order higher to see how the convergence pattern is. And with that, I would like to stop.